In this video, we'll start to learn about organohalide reactions. When we start looking at our organohalide reactions, we're going to really focus on first the organometallic reactions. And those include our Grignard reaction, our Gilman reaction, and our Suzuki reaction. Then we're also going to briefly look at oxidation and reduction reactions in the context of organic chemistry. So first, starting with our Grignard reaction. Grignard reactions are often used to synthesize alcohols. So they go from an alkyl halide to an alcohol. And to form the Grignard, we need the alkyl halide, which is treated with magnesium metal. So we can start with any of these alkyl halides. It could be a primary, secondary, tertiary, an alkenyl, or an aryl. And then as long as it's an alkyl halide, it reacts with the magnesium. It reacts with the magnesium to form our Grignard reagent. So we always have to form our Grignard reagent right before we use it. We can also use any of these halogens. It could be chlorine, bromine, or iodine. So there's a large combination we can do with our Grignard reactions. And so one important thing about our Grignard reactions is the difference in electronegativity between the carbon being 2.5 and the magnesium is 1.3. This means the magnesium carbon bond has a significant ionic character. It also indicates that our carbon is actually where that partial negative charge is. So in this case, we form our carbanion, which is our negatively charged carbon. It also means since the carbon is a negative charge, it's going to act more as a nucleophile in this case. So it's going to be the one that does the attacking instead of being attacked like we usually have been doing. So now let's start looking a little bit at this Grignard mechanism. So first, let's say we have an alkyl halide, and I'm going to react it with magnesium and ether, because we always need to form that reagent first. What's going to happen is the magnesium is going to insert itself between the carbon and the iodine. So once it does that insertion, now we have the magnesium there that's connected to the carbon plus the iodine. So this forms our Grignard reagent. The Grignard reagent then goes on to the next step. And it reacts with a carbonyl. So here we have it reacting with our ketone. So what's going to happen is, since this carbon is a partial negative and our magnesium is a partial positive, the carbon is going to go and attack the carbonyl and move electrons up to the oxygen. So let's highlight the carbons that actually attack. So the red one there is our new addition. And then our magnesium is next to the oxygen to help stabilize it because the magnesium is a positive charge. After this happens, we add water, and then our oxygen will come and grab a hydrogen from water to neutralize. So we end up with our alcohol. Plus the addition of that new alkyl group. So our Grignard can attack different types of carbonyls. We can have our Grignard reagent that we just made. It can react with an epoxide. Step 1. Step 2 is adding that water. And what'll happen with the epoxide is it'll go and open up the epoxide. So our partial negative charge there will go and attack the less substituted side of our epoxide to open it up. And then we have the addition of the new carbon chain there. Our OH group appears after we add that water. It can attack ketones that we just saw. It can also attack aldehydes. They go through the exact same mechanism as ketone. So make a little note of that here. Aldehydes, the aldehyde does the exact same mechanism as a ketone. And then it can also attack an ester. So again, if we start with our alkyl-halide, that we've turned into a Grignard reagent, and now I have an ester. I'm actually going to have to use 2 equivalents of my Grignard reagent to react with that ester. So it's going to add twice. And that's because when we do the first addition, so we'll make a little note. Our first addition of our Grignard reagent, we form this particular compound where we have our alkyl group we've attached. There we go. We have our alkyl group we've attached, and it ends up actually forming a ketone after the first addition. The oxygen group here, that gets removed during the first addition, and we reform the ketone. Then with our second addition of Grignard, since we have a ketone, we know our Grignard reagent's going to react with it and form an alcohol after we've added the water, plus our 2 groups. So esters, we'll make another little note here. Esters have 2 additions of our Grignard reagent. So we actually add 2 alkyl groups at that point instead of just 1. One thing to note, it does not react with carboxylic acids. And so let's briefly look at that one real quick. So if I have my carboxylic acid, and I have my Grignard reagent. Since that carboxylic acid has our acidic proton, And this carbon has a really large partial negative. It's almost a complete negative. That partial negative is going to go and attack the hydrogen. So that partial negative attacks the hydrogen and moves electrons on to the oxygen. Which means we then end up with our carboxylate and our ethyl group and our ethane. We don't actually get the Grignard to react with the carbonyl part. Instead, the acid-base reaction is a quicker reaction. So an important thing to note for Grignard reactions, you cannot have acidic hydrogens present. I'll underline that. So we cannot have acidic hydrogens present during Grignard reaction, which means no carboxylic acids, no alcohols, and no water. So you can't have these around when you do a Grignard reaction. If any of these are around, the hydrogen associated with that oxygen there is going to react with the Grignard reagent instead. So if you wanted to turn a Grignard into an alkane, adding these is a good way to do that. So it turns our Grignards into alkanes. So we only want to do that if we want the alkane. And generally, water is our cheapest reagent, so we tend to use water for that. Another organometallic coupling is our Gilman reactions. And so in Gilman reactions, we prepare them similar to the Grignards, except for Gilman, instead of using magnesium, we use lithium metal, and that'll react with alkyl halide to form an alkyl lithium reagent. That means that the carbon the lithium is attached to is very basic and also considered nucleophilic. So it's considered a nucleophile. So it essentially has that negative charge on it, and our lithium is a positive charge. And then the second step is we form a lithium diorgano copper compound. That would be our full Gilman reagent right here. So we'll need 2 equivalents of our lithium here. We'll need 2 equivalents of our alkyl lithium, which means we need 2 equivalents of our alkyl halide to start with. That reacts with copper iodide to form the Gilman reagent. Gilman reagents can undergo a couple types of couplings. The first type of coupling it can undergo is with alkyl halides. So Gilman reagent will react with our alkyl halide to form a longer alkane chain. And so this is very useful for forming carbon-carbon bonds, because I can take my alkyl halide and my Gilman reagent, and now I've extended the chain for the alkyl halide. And it reacts with alkyl groups, alkene groups, and aromatic groups. So this is one way we can add some sort of alkyl group to an aromatic ring. As I start with something like iodobenzene, reacted with my Gilman reagent, and now I've added a methyl group to it. I've created toluene. And you can see these are generally very high yielding reactions. They work very well. And so if we look at the mechanism for it, So if we look at the mechanism for it, we have our alkyl halide, and I have my Gilman reagent. What's going to happen is the Gilman reagent is going to do what we call an oxidative addition. So it's going to come and insert itself in between the carbon and the iodine. So then we have it inserted in between, and we have our two methyl groups still around the copper there. What then happens is one of the methyl groups does a methyl shift and migrates over to the carbon from our chain, which then moves electrons onto the copper and kicks out the iodine. This leaves us with our methyl group now attached to the chain where the iodine was, and our copper with its one methyl group plus lithium and the halogen. Our Gilman reagent can also react with what we call alpha beta unsaturated ketones. So that'd be if we had a ketone that has a double bond essentially on carbon 1 and 2 away from that ketone. And the interesting thing with this one is the Gilman reagent won't actually attack the ketone part. Instead, it goes after the carbon at the end of the double bond. So it leaves your ketone alone and adds the methyl group down here, which is very different than if we had a Grignard reaction. That Grignard reaction, make a little space. That Grignard reaction will actually react with the ketone and put the methyl group on the ketone part. So now we can kind of play with where we get that methyl group attached. Gilmans can also react with acid chlorides. So if I have an acid chloride, and I do a Gilman on it, fix my acid chloride, it'll turn that acid chloride into a ketone with my methyl group attached where the chlorine was. Now let's briefly look at our last organometallic reaction, the Suzuki reaction. So in the Suzuki reaction, it's a coupling reaction of an aromatic or vinyl substituted boronic acid with an aromatic or vinyl substituted organohalide. So this is one way we can connect two different aromatic rings together or two different double bonds together. And that's achieved through using our boronic acid and our alkyl halide in the presence of palladium with a triphosphate ligand. And a palladium catalyst. Now the mechanism for a Suzuki is what we call a catalytic cycle. And within that catalytic cycle, first what happens is our aromatic halide enters the cycle. It then goes and causes the palladium to insert itself between the aromatic ring and the halogen. This then continues on with the second aromatic ring and the boronic acid entering into our cycle. The palladium then inserts itself between the two aromatic rings, kicking out on. Then what happens is the palladium exits the cycle, the two aromatic rings join together, and they leave, which allows the palladium to restart the catalytic cycle over again. And for our class, you don't have to remember this particular mechanism, but this is how a Suzuki reaction works and does a palladium coupling of two aromatic rings. So now let's briefly talk about oxidation and reduction reactions in context of organic chemistry. So with oxidation, really that's a decrease of electron density around the carbon. So oxidations form carbon-oxygen bonds, carbon-nitrogen, or carbon-halogen. It also can be considered an oxidation when we break a carbon-hydrogen bond. So the less hydrogens we have on there, the more oxidized the carbon is. Reduction is the opposite process. So in reduction, we're increasing the electron density around our carbon. So that's when we form carbon-hydrogen bonds or carbon-carbon bonds. And we're breaking carbon-oxygen, carbon-nitrogen, or carbon-halogen. So an example of an oxidation reaction would be a radical halogenation. So if we did a radical halogenation, what we're doing is we're removing a hydrogen and we're adding a halogen. Doing that is an oxidation. It's an oxidation step, so it's considered an oxidation reaction. An opposite process, if we do a Grignard reaction and then we use water instead of any other group, I turn my halogen into a hydrogen. So I'm doing a reduction. Another type of reduction is when we do a hydrogenation. You're going from a double bond and you're adding hydrogens. Since we add hydrogens, we're reducing the carbon. Since we add hydrogens, we're going through a reduction. And so some oxidation reductions. When we think about oxidation levels of the carbons, an alkane, a straight alkane, that would be a very low oxidation level because there's as many hydrogens on there as we can possibly get. So this is considered a fully reduced carbon. Double bonds are slightly less reduced or slightly more oxidized than the alkane. Or you can add an alcohol, chlorine, nitrogen. Triple bonds are even more oxidized because we've lost even more hydrogens. Same thing with carbonyls, or if we had two chlorines or double bond to a nitrogen, make an amine. If we have a carboxylic acid, that's even more oxidized than just the carbonyl. Or if we create a nitrile, that's more oxidized than our amine. And the highest oxidation states you can get are the ones with no hydrogens on the carbon. So that would be our carbon dioxide or carbon tetrachloride. Those are some of our highest oxidation levels for carbon that we have. And so now you guys should be more familiar with some reactions with alkyl halides and also what an oxidation and reduction reaction are in terms of carbons.